Okay, so we're going to get started. So here's our new thing for today. We are going to begin introducing the last meaningfully different kind of integral, and it appears that my this is interesting. Okay, seems to want me to type over my slides. I don't know why it's asking me to do that, but hopefully it won't do that going forward. So we're looking at the last major type of integral. And when I say that, well, what could that really be about? Well, only a couple different things, really. Now, we've already seen a lot of different kinds of integrals so far. So just to recap, we've seen single integrals on intervals of the number line. We've seen double integrals over regions in two-dimensional space. We've seen triple integrals over regions in three-dimensional space, solid regions in three space. And we've seen line integrals, or integrals over curves, and over curves in R2 or R3, two space or three space. And those line integrals can either be of scalar functions or vector fields. Either is possible. In this case, we're talking about a surface integral. Now, a surface integral is well, as the name suggests, it's an integral over a surface. So this is the last major kind of thing we can look at. We've seen integrals over two-dimensional and three-dimensional objects, and now it's time to look at a two-dimensional object sitting inside of three-dimensional space. This is what a surface integral is. And as with line integrals, there are really two different kinds of surface integrals. You can either have surface integrals of scalar functions or surface integrals of vector fields. And they mean very different things. Surprise, surprise. Let's look at the scalar functions first. So if you want to take a double integral, a surface integral of a scalar function, well, what would that be? Well, if your function is just the constant f equals 1, it turns out that that's going to be just the surface area of S. Some people actually define area that way, and we'll see what ds is in a little bit. Now, on the other hand, if f is the density of some quantity, then what that tells you is the total amount of stuff that quantity has on the surface. Now, for a classic example of this is F could be the mass of some heterogeneous sheet. It could also be the charge on a sheet, in which case the double integral represents the total electric charge over some sheet, or magnetic charge, for example. It could be the amount of some mineral on the surface of the Earth or the surface of some other planet, and so on and so on. Yeah, it could also be heat. You could also look at the total heat over some surface, and all different kinds of things. Now, the ds notation means with respect to surface area. So now it's important to recognize that you've got d capital S, which is with respect to surface area, versus d little s, which is with respect to arc length. So capital S refers to surface area, little s refers to arc length. So how do you actually calculate one of these things? Well, like with line integrals, the idea basically is going to come down to how do you approximate area? So what do you do with the fxyz ds? Well, the fxyz, okay, that's just going to be f of ruv. Ruv is the parametrization of the surface. So you plug in the point into f that you're going to be parametrizing with. So that's just f of r of u and v. What about ds? ds is going to turn out to be Ru cross Rv magnitude dA. And where does that come from? That comes from the fact that the parallelogram, the area of the parallelogram, is the magnitude of the cross product of the vectors when you interpret the vectors as the edges of the parallelogram. So this figure on the left-hand side, that's all the way back from chapter 12. We've seen that before, right? That's, that parallelogram has area given by the magnitude of that cross product. Well, when you're approximating the area of the surface area of some surface, you're going to approximate it using these parallelograms depending on your parameterization. So what we really want to do is have a nice way of calculating the magnitude of that parallelogram, and you do that using this cross product of the velocity vectors of these parameterizations, Ru cross Rv dA. So that comes down to the approximation of what the area is. Much like the magnitude of r prime, magnitude r prime is kind of ish an approximation of length, because speed times time gives an approximation of distance. So it's the same principle, basically. Now, what happens when you actually try to calculate the surface area of some surface? Well, once again, you can interpret this as the mass of a surface with a constant mass density given by fxyz is always equal to 1. Which is to say, you want to use this formula, fxyz ds is the double integral of f of ruv times magnitude ru cross rv. But if fxyz is constantly 1, if it's constant 1, then I know what fruv is. fruv is still going to be just 1. It's just going to be the function 1. And oh, that's a typo I'm now noticing in my in my notes. That should be, or in that slide, that right there should be a double integral, not a single integral. And when I upload these notes to Canvas, then I'll fix that. That should be a double integral over that thing. But that's exactly the formula that we saw for surface area. So so when we consider surface area, we looked at before, well, the surface area is just the magnitude of the cross product of the derivative vectors for the parameterization. But that immediately falls out of this interpretation of the double integral, the surface area integral of the constant function 1. So it's the same exact idea. It's good when two different approaches to a mathematical result give the same result. So let's do an example of this. Let's calculate the surface integral xyz ds, and s is the surface that's parameterized by u cosine v, u sine v, u. This is what's known as a helicoid. It's sort of like a gigantic spiral ramp for u going between 0 and 1, and v going from 0 to pi over 2. So let's do this. Well, again, just in general, the first thing you want to do for anything like this is to write down the formula. Now, okay, in the past I've said that the first thing you want to do is to draw a picture. In this case, a picture is going to be hard to draw in 3 dimensions, so we're not going to worry about that quite yet. But what we are going to do is write down what the formula is that we want. The formula that we want is the double integral over s of fxyz ds. That's the double integral over d of f of, I'll write it as xuv, yuv, zuv, times the magnitude of ru cross rv dA, where dA in this case, I mean du dv. So we're going to need to know what the derivatives ru and rv are. So ru is going to be cosine v, sine v, 1. And rv is going to be negative u sine v, u cosine v, 0. So you take the cross product of these things, ru cross rv. So you've got your usual I, your j, and your k, your cosine v, sine v, 1, negative u sine v, u cosine v, 0. So you take your cross product, and what does this come out to? This is going to come out to negative u cosine v I minus, now just to be safe with the minuses, it's minus 1 times negative u sine v, but you negate that again. So it's negative u sine v. So it's still going to be negative once you come out that other side. And in the k term, cosine u cosine squared plus u sine squared. So that's going to be plus u k. So the whole thing comes out to negative u cosine v minus u sine v, I, j, plus uk. And now we take its magnitude, ru cross rv, square root of, oh, and by the way, before I keep going with this, once again, you can always check this. You can always check your own work. So in this case, you take that dot product with RU, what would you get? Negative U cosine squared minus U sine squared plus U, negative U plus U, that's 0, which is good. I'm just taking a dot product in my head, basically. I'll use the laser pointer. What I'm saying here is that you can take cosine V times negative U cosine V, negative U cosine squared, minus sine times U sine, or in other words, minus U sine squared, so that just becomes U, plus 1 times U, so that's 0, so that's good. Negative, so then you've got U squared cosine V sine V, minus U squared cosine V sine V, plus 0, so that's going to be 0 too. So this does work out the way you want it to. You can always check your cross products. That's the good news. I wanted to remind everyone of that option. So you take your magnitude. This is U squared cosine squared V plus U squared sine squared V plus U squared. Whole thing comes out to root 2U squared, or in other words, root 2 times U. Now, meanwhile, we're also going to need to know what f of r of uv is. Strictly speaking, it's not really proper of me to include this arrow there because this doesn't follow from this, but it's an important ingredient which we're also going to need. F of r of u of v is going to be, in this case, u cubed sine v cosine v, right? U cosine v times u sine v times u, x times y times z. Now we're ready to actually calculate this surface integral. So what is this? This is the double integral over d of root 2 u to the 4th sine v cosine v dA. This integral is separable and it's being taken over this rectangle, so this isn't hard to calculate. You can use our little trick here. Integral from 0 to 1 of root 2 u to the 4th du times integral from 0 to pi over 2. 0 to pi over 2 sine v cosine v dv. And now you're off to the races. These are, neither of these are terribly difficult integrals. The first one is is root 2 over 5 times 1/2. Actually, I'll do this a little more step by step. 2 over root 5 u to the 5th for the first integral times 1/2 sine squared v, and u is going from 0 to 1 and v is going from 0 to pi over 2. In this case, in both cases, the zeros just go away and you're left with 1 on both sides. So this comes out to root 2 over 10. And that's our final answer. All right, so questions for how we got to this point, how we got to this result. It's mostly just plugging and chugging so far. Right. It's always good to write out what your formula is to make sure that you can actually see everything that you're trying to do and everything that you're going to have to work with. So these are good habits to develop. Now, every now and then, your surface that you'll be working with will actually be a graph. And if it's a graph, we looked at last week how to parameterize surfaces that are graphs. You can either use RUV equals UV GUV, or RXY equals XY GXY. I mean, the universe doesn't care whether or not you're using u and v or x and y. It's the same exact thing either way. But it turns out that this magnitude of the cross product is given by the square root of 1 plus gx squared plus gy squared. If you like memorizing a bunch of formulas, personally I don't. This is this is not something that I like to do, but it's something that some people like to do. But if you like memorizing formulas, then this is one that's available to you. You can say that this is just fxy gxy times the square root of 1 plus gx squared plus gy squared. Now, I don't think this is easier personally. I don't, Stewart describes this as a shortcut. I don't really consider this much of a shortcut personally. I just think that this is just one more thing to memorize. For me, it's easier to just think about, oh, well, I know how to parameterize graphs. And if I know how to parameterize graphs, then this falls immediately out of the regular formula. But if this is easy for you, or if this is easier for you to do it this way, then by all means, be my guest. So what exactly is this? What's the significance of this RU cross RV? Well, we think of it as sort of like a stretch factor. So what's going on when you parameterize a surface is you have your flat space, and we literally do call it flat space, of u and v, and you've got some region which we usually denote by d, that's sitting inside of that flat space, and that region is broken up into these squares, right? It's broken up into these squares or rectangles or whatever you like, and assuming I'm a good artist, which I'm not, but if I were, then all of these squares would be the same size. I'm going to see if I can be a little more self-respecting in terms of my artwork and try to make them a little bit closer to each other. That's better. So, so you take your flat region D, and what you're doing at this point is you're taking this region, and you're sending it along. You're applying, if you take some point UV in it, you're sending it through R into three-dimensional space. And in three-dimensional space, you've also got got this region here. Actually, I'm going to see if I can do that slightly differently. Trying to make some super curved and warped up surface. It's really weird. This is kind of hard to do. But basically what's going on here is you've taken your space in flat space and sent it into three-dimensional space, which we usually denote with our x, y, and z. And what ends up happening is that when you do that, usually, very often the parameterization you'll use will stretch and contort, either stretch out or shrink down those rectangles. And it's much more common for it to stretch and shrink them down or do something like that than it is for them to stay exactly the same area. In fact, if they stay exactly the same area, that's extremely rare and special. And that pretty much only happens if the thing that if the result, the final surface that you're doing is itself flat in some sense. So if it's curved up in any interesting way, you're gonna have some stretching that's going on. Just how much stretching? Well, the amount of stretch or contraction or whatever the case may be, that's given by this factor magnitude RU cross RV. That tells you how much your rectangles are stretching out in each case. And again, we interpret this as sort of like an approximation of the area. So as an example of this, let's suppose that we want to take the double integral of x squared z plus y squared z ds, where s is the hemisphere that's given by x squared plus y squared plus z squared equals 4, for z being positive. Okay, so once again, we want to know what RU is. So what's RU? Well, S is the hemisphere. So there are two different ways we can do this. here's one option. One option is, okay, well, this is a hemisphere. And since it's a hemisphere with z is positive, our surface S is a graph of a function. So you can write this as the graph of the function g, not z, sorry, gxy equals root 4 minus x squared minus y squared. For x squared plus y squared greater than or equal, not greater than or equal to, less than or equal to 4 to ensure that that thing inside of the square root is a real number. So that's one thing that can happen. That's one way we can do this. And if we do it that way, as we said, gx is negative x over root 4 minus x squared minus y squared. Gy is negative y over root 4 minus x squared minus y squared. So in this case, the magnitude of Rx cross Ry, using our graph trick, if you remember it, is gx squared plus gy squared plus 1. Or in other words, this comes out to square root of x squared plus y squared over 4 minus x squared minus y squared plus 1. Or in other words, doing this one more time, this is going to be, this is going to come out to, just doing this whole thing together, 4 over 4 minus x squared minus y squared, all under one big square root once you actually add those things together. Or in other words, 2 over root 4 minus x squared minus y squared. And meanwhile, f of xy gxy would be x squared root 4 minus x squared minus y squared plus y squared root 4 minus x squared minus y squared. So the double integral over S of x squared z plus y squared z ds, that would come out to the double integral over d. Now what is d? We don't know what d is yet, but we'll figure that out. It's the double integral over d of 2 times x squared plus y squared dA. X squared plus y squared because the root 4 minus x squared minus y squared gets canceled out when you multiply it by magnitude Rx cross Ry. Now, by the way, what is d? Well, d, we know that d is all x and y. To move around some of my windows a little bit. It's all dxy is all x and y, so that x squared plus y squared is less than or equal to 4. But you can do that in polar coordinates, which is, I think, a little bit easier in this case. This would be, it's all points, so that r is less than or equal to 2. And theta can be anything. So in other words, this is going to become the integral from 0 to 2 pi of the integral from 0 to 2 of 2r cubed dr d theta, which comes out to, after all of the, the dust settles, 1/2 r to the 4th from 0 to 2 times 2 pi, or in other words, 16 pi. All right, so that's one approach to doing this problem. You can parameterize this surface as a graph. But that's not the only way you can do this. That's not the only way to solve this problem. This worked, and it wasn't terribly difficult, but sometimes working with square roots can be a little bit frustrating and obnoxious. So maybe you don't want to have to deal with that. You might want to avoid that. That's okay. There's a way to do that. So let's see another way of doing this problem. Before I erase everything, are there any questions on how I did this? Okay. So here's another way of solving this problem. Our second approach is to use spherical coordinates. Since z is always positive, we can write this as x is, and the radius is always 2, is 2 root 4. So x you can write as 2 sine phi cosine theta. Y is 2 sine phi sine theta. And z is 2 cosine phi. Let me try writing that phi a little bit better. There we go. So if that's how you want to do it, then once again, you can figure out what the magnitude of that cross product should be. R phi cross R theta. Differentiate with respect to phi, you're going to get 2 cosine phi sine theta. Oh, sorry, I did that in the wrong order. Differentiate with respect to phi, you get 2 cosine phi cosine theta. 2 cosine phi sine theta. Negative 2 sine phi. On the other hand, you can write negative 2 sine phi sine theta, 2 sine phi cosine theta, theta, 0. I like writing personally, I like writing the ijk at the end because these can be kind of long entries. So what does this come out to? This is going to come out to 2 sine squared phi cosine theta, I, minus, actually plus in this case, plus, oh, I'm sorry, that should be 4, not 2. Oops. 4 sine squared phi cosine theta, plus 4 sine squared phi, sine squared phi sine theta, j. And in the k direction, plus 4 cosine phi sine phi k, because you get the cosine squared plus sine squared, that's going to just result in 1. Now, strictly speaking, it's the magnitude of all of this stuff, so I forgot to include that part. So it's the magnitude of all of that, which comes out to, all right, this is 4 times the square root of sine to the 4th cosine squared theta plus sine to the 4th sine squared theta plus cosine squared phi sine squared phi. Which is going to come out to sine to the 4th, which is going to come out to 4 times sine squared phi. I have to move around my windows again a little bit. Sine squared phi sine squared phi plus cosine squared phi, or 4 times sine phi. And you know it's positive because phi is always between 0 and pi, or in this case, since it's only z is the upper half, since z is only the upper half, phi, we remember how spherical coordinates work, we're going to have that theta is between 0 and 2 pi going all the way around, but phi is only going halfway down. So phi is going from 0 to pi over 2. By the way, some of you may notice that that's the same thing as rho squared sine phi. So just to remind everyone, you know, that's what the stretch factor is in spherical coordinates, rho squared sine phi. There's a reason that, you know, that comes from somewhere. Okay, so now we need to find out what f of r of phi and theta would be. And to do that, well, we know that that's x squared z, or in other words, sine squared phi cosine squared theta cosine phi, plus sine squared phi, sine squared phi sine squared theta cosine phi, or in other words, sine squared phi cosine phi. So now we're ready to calculate the triple integral over the surface of x squared z plus y squared z ds. Let me just make sure that because I've got some windows obscuring. Yep, that's right. So, so that's going to become integral from 0 to pi over 2, integral from 0 to 2 pi of 4 sine cubed phi cosine phi d phi d, d theta d phi. Because phi is going from 0 to 2 pi. And in this case, and if you go through this, what's this going to become? Well, it's just sine to the fourth phi, sine to the fourth phi times, from 0 to pi over 2 times 2 pi, which, and I think I made a mistake somewhere. Give me a second. I see what the mistake was that I made, and it was in calculating f of r of phi and theta. These are, here's the issue. So let me try this again. The issue was x is 2 sine phi cosine theta. So in fact, f of r of phi theta actually is going to become 4 sine squared phi cosine squared theta cosine phi times actually 8 in that case, not 4. Minus 8 cosine squared. Is it minus or is it plus? Sorry, plus 8 sine squared phi sine squared theta cosine phi. Or in other words, there we go. Or in other words, 8 sine squared phi cosine phi. There we go. That's better. And now with that in mind, we can say the double integral over s of x squared z plus y squared z ds. Now I can say this is going to be the integral from 0 to pi over 2, integral from 0 to 2 pi of of 16 sine cubed phi cosine phi, because you're multiplying f of r of phi theta by magnitude r phi cross r theta. D theta, d phi. There we go. Now this is going to become 4 sine to the 4th of phi from 0 to pi over 2 times 2 pi, which would be 8 pi. Well, that's still not what I had last time, but probably must have made a mistake somewhere with getting some factor of 2 that I missed, either in this process or the last process. One of the two of them I made a mistake in, but when I upload the notes for these slides, I'll have fixed this error. But I'll move on for now. So sorry about this, but the point is, these are two different ways of solving this problem. You can either use spherical coordinates, or you can consider S to be a graph. Either of these is a perfectly valid way of solving this problem. So I'll move on for now and not continue to embarrass myself with whatever is going on here, but I will upload the slides for this and then figure out what went wrong. Okay, so now that's not the only way that's not the only kind of surface integral. As I mentioned before, there are two kinds of surface integrals, one of which is for scalar functions, which we just did, and the other is for vector fields. So what's the double integral, what's the double surface integral of a vector field? We interpret this as the flux of the vector field across the surface. So now in one of the physics classes that we offer at Penn State, you would have learned about the flux of the electric field. So if you consider F to be the velocity field of a fluid, then the flux is the volume flow rate across the surface. I like to interpret this as, for example, hosing down a mosquito net. So like you've got some mosquito net that's dirty because you've killed a bunch of mosquitoes on it, and you want to hose it down. Well, you hose it down, and some fluid passes across it. But you don't want to hose it down directly head on, because if your hose is too strong, you'll end up breaking your net. So you hose it at an angle which decreases the flux across it. So that's what we think about when we think about flux of a fluid across a vector field. Now an important thing to bear in mind here is that flux as integrals, flux means that you're going from one side of the surface to the other, which means that sort of implicit in that characterization is the notion that your flux has to have some clearly defined notion of a side, like it has to have a top side or a main side in some respect. So so for the top side of the flux, what does that really mean? Well, it means that your surface has to be oriented. Your surface has to have two different sides to it. Now you might be thinking, actually, so how do you define a side? The way we define a side is we choose a unit normal vector n everywhere on the surface. We call that the normal vector field over the surface. Now, the important thing about this normal vector field is it's perpendicular to the surface at every point. Its length is 1, and it varies continuously. So in other words, this is like saying that I'm only going to paint one side of this surface. I'm going to paint the side of the surface that has the arrow on it, that has the upward side, the upward normal vector. Now, can you always do this? Well, no, not every surface has two sides, which is weird, but it's true. Take, for example, a Möbius band. A Möbius band, if you imagine you're at this point P, and the unit normal field at P is pointing inside of the band. But as you move around, counterclockwise from our perspective, as you move around the band, you eventually are going to end up on the flipped side. So you get across to the other side of P, and all of a sudden you're on the other side. So that vector field, that normal vector field, cannot vary continuously. So that's not an orientable surface. You can't talk about vector calculus, you can't talk about flux integrals over that surface in a meaningful and reasonable way. So how do you actually choose? How do you actually find this normal vector? Well, the way that you do it, well, the important point here is that it's perpendicular at each point and it varies continuously. Well, to make it perpendicular at every point, simple enough, you define it to be the vector that's orthogonal to two different tangent vectors of the surface. Well, the easiest two tangent vectors to use are RU and RV, and a vector that's orthogonal to both RU and RV is the cross product. So you just make the cross product of RU and RV and multiply it by and divide it by the magnitude to ensure that it's a unit vector. And if you do that, you get RU cross RV over magnitude RU cross RV, and that's what we're going to choose for our vector n. And it turns out that if you do it that way, then you just get RU cross R, then the vector field, the integral, becomes the double integral of f of r of uv dotted with RU cross RV dA. Where does this come from, by the way? Why is that? Well, it's actually not very hard to work out why that has to be the case. Because if you take your double integral over s of f dot ds, to make sure to bold s, we write it with an arrow over it. Well, that's the same thing as the double integral over this surface of the function. Oh, I forgot something important there. F dot nds without an arrow, right? We said before that ds, the big S with an arrow over it, the vector differential, is nd is the normal vector times a small change in surface area. Well, that's going to be the double integral over S of f of r uv dotted with, now what's n? N is, oh, not S, I'm sorry, D, now the domain of the parameterization. N is RU cross RV over magnitude RU cross RV times ds, right? But ds, we remember, is magnitude RU cross RV dA. Now here in this case, we're saying that, now here in this instance, we're saying that f of xyz is the scalar f dot n, which is a scalar, so that makes sense on this surface, times magnitude RU cross RV dA. That just comes from the same old system that we had before when we were looking at scalar surface integrals. Well, the RU cross RV magnitudes cancel out, and we're left with exactly what we claimed we would have, which is f of RUV dotted with RU cross RV dA. So that's where this comes from. That's the formula that we're going to use here. All right, questions about where this formula came from? So how do you calculate the flux across this object? Well, what we're going to do here is RUV. So again, it's always a good idea to write out what your formulas are. So in this case, the formula that we want is the double integral over your surface of f dot ds. This is the flux. Double integral over d of f of r uv dot ru cross rv dA. Now in this case, f of RUV is VI plus U sine V J plus U cosine V K. And RU cross RV Just take the derivatives and do the cross product. This comes out to cosine v, sine v, 0, negative u sine v, u cosine v, 1, I, j, k, which will be sine v, I, plus cosine v, or sorry, minus cosine v, excuse me. Eraser. Erase. Minus cosine v, j, plus u, k. So you take the dot product of those things, f of r of u v, dotted with ru cross rv is v sine v minus u sine v cosine v plus u squared cosine v. So you integrate this thing for the flux. Integral from 0 to 1, integral from 0 to pi, v sine v minus u sine v cosine v plus u squared cosine v, and dv du. And what's gonna end up happening is that you're gonna anti-differentiate sine v cosine v to 1/2 sine squared, which vanishes at 0 and pi, and cosine v is gonna anti-differentiate to sine v, which again vanishes at 0 and pi. So and the first term doesn't have a unit at all, so this whole thing comes out to integral from 0 to pi of v sine v dv. Unfortunately, I have to do this by parts, which I'll do quickly as just an example of what this would look like. Let's say we're going to leave the v un-anti-differentiated. So that'll be v and sine of v. Well, that will anti-differentiate that to negative cosine. So it'll be v times negative cosine v from 0 to pi plus, and now you differentiate v, which is much easier, integral from 0 to pi of cosine v dv, which comes out to negative v cosine v from 0 to pi plus sine of v from 0 to pi. That's going to vanish, or the second term is going to vanish. And this just leaves us with 2 pi. Actually, no, excuse me, not 2 pi, just pi, because v is 0. Let me undo what I just did. After going through the antiderivative, which you have to do, which you have to do by parts, but it's not terrible. Okay. So thank you, everyone. We will end with this example for today. And then for recitations this week, we'll do lots of examples of surface integrals so you can begin getting a sense of what we're going to look at. We do have a lecture tomorrow as well on sort of a parallel to Green's theorem, but it's a parallel to Green's theorem for surfaces in space, in three-dimensional space, not just regions in two spaces. So we'll have that to look forward to. All right. Thank you, everyone. We will talk to you later.